Ear Anatomy and the Steps of Hearing by Kaitlyn Gonzalez. Disclaimer. Before we begin, I would like to say that all experiments were conducted ethically. Participation was voluntary. Participants were provided with informed consent. Researchers maintained participant confidentiality, and no mothers were harmed in the making of this video.
Mom! So loud, you scared me!
I'm sorry. Why was my mother able to hear my voice? Why was she able to interpret the loudness and pitch of my voice? How was she able to distinguish my voice from that of the telenovela that she was watching? These are all questions that understanding ear anatomy and physiology will help solve. Anatomy surrounds the structures or parts of the body, whilst physiology hones in on how those parts work together for a specific focus. Let's begin with a closer look at our ear's anatomy, focusing on the structures of our ear. To begin, let's start off with the outer ear. The visible part of the ear and ear canal, typically referred to as one's cartilage, is known as the pinna. Moving inwards, sound waves travel into the ear through the oval canal, reaching the eardrum, and three tiny bones known as the ossicles. The ossicle bones are called the malleus, incus, and stapes. The seashell-shaped object is known as the cochlea, which is below the semicircular canals, and the auditory nerve. This nerve will transmit information into the auditory cortex of the temporal lobe in the brain. Before we talk about hearing physiology, let's briefly go over sound waves. A sound wave is a wave of compression in which a sound is disseminated into an elastic medium such as air. Each sound produced has a different type of sound wave. The frequency of a sound wave determines its pitch, whilst its amplitude or height will determine how loud or quiet the sound is. Thinking back to our beginning questions, the interpretation of different sound waves allows for my mom to differentiate between the television and my loud voice. Pitch. There are two main theories that determine how we are able to differentiate between different frequencies of sound: place theory and frequency theory. Place theory suggests that we hear different sounds because different places are triggered within our cochlear's basilar membrane. However, this theory only explains high-pitched sounds because when conducting experiments, low-pitched noises were not easily located in the cochlea. On the other hand, frequency theory states that the rate of nerve impulses traveling up the auditory nerve match the frequency of a tone. However, this theory only explains lower-pitched tones, as an individual neuron cannot fire faster than 1,000 times per second, but we can sense frequencies above that. These two theories work together to help us understand perceptions of pitch. Physiology. To begin, a sound wave or an auditory input enters the pinna into the oval canal. The sound waves then hit the eardrum, which begins to vibrate. This vibration reaches the ossicles. The malleus, incus, and stapes work together in a piston-like system to help move this vibration further down the auditory process. To remember what a piston is, think of the game Minecraft. This transmission then helps reach the cochlea, which contains a basilar membrane. The cochlea's basilar membrane is lined with tiny little hair cells that, when moved, trigger an impulse in the auditory nerve. Your brain interprets loudness from the number of hair cells that were activated. When a loud noise, for example, is passed by the hair cells, more of them tend to move, triggering the auditory nerve to send interpretations of loud to the brain. When talking about hair cells, do not picture the hair that is on your head. Picture seaweed. These hair cells are thousands of microscopic structures that naturally sway back and forth with the fluid within the basilar membrane, like seaweed in the ocean. When a sound wave comes through, these hair cells begin to sway and vibrate, sending an electrical impulse into the auditory nerve. The auditory nerve carries this impulse into the brain for the final step of hearing, interpretation. Here's a quick little song to help you remember the steps of hearing. You're on the phone with your girlfriend, she's upset. She's sending auditory sound waves into your ear. These sound waves pass right through the oval canal. They then hit the eardrum, vibrating. Vibrations get pushed through the piston, and now you reach the most important cochlea. It's basilar membrane lined with hair cells. These vibrations will sway them back and forth. Moving these hair cells will send an impulse that your auditory nerve will send to your brain. If you can hear that I'm the one who understands how we've been hearing all along, so why can't you see? That's how hearing works, baby. That's how hearing works. What about hearing loss? There are two main types of hearing loss: sensory neural hearing loss and conduction. Sensory neural hearing loss is caused when there's immediate damage to the cochlea and auditory nerve. This can be caused naturally through aging. As we get older, our hearing worsens, but can also be caused through noise damage and side effects from drugs. The ringing noise you sometimes hear is your body's way of signaling pain to alert us from a possible sensorineural damage. The second type of hearing loss, conduction, is more mechanical. This can be caused by a blockage such as axis earwax or a foreign object, a burst in eardrum, or simply congestion from an allergy. Meaning it damages the mechanical systems that transport sound waves into the ear. When dealing mainly with conductory hearing loss, a cochlear implant may be used to bypass the mechanical damaging. A cochlear implant is a medical device that interprets sounds and translates them into auditory nerves through electrical impulses. It is important to note that a cochlear implant is not effective if the cochlea is damaged. That's why it can only bypass conduction-based hearing loss. A statistic from the National Institute of Deafness states that non-Hispanic white adults are more likely than adults in other racial or ethnic groups to have hearing loss, and non-Hispanic Black adults have the lowest prevalence of hearing loss amongst adults aged 20 through 69. I hope today's lesson helped you understand more about ear anatomy and the steps of hearing, and just how my mom was able to determine the different pitches, loudness, and just hear my loud voice in general when she was listening to her telenovela. Thank you.